Hello learners, welcome back. I am Rajat Tiwari, lecturer, University Teaching Department, Chhattisgarh Swami Vivekanand Technical University and subject matter expert for this course. In today's session, we will dive into the world of acoustic and sound insulation. Our focus will be on understanding how different materials and design strategies can effectively block or absorb sound, thereby reducing noise pollution and improving sound quality within spaces. This session is designed to equip you with a thorough knowledge of the principles and practices that ensure optimal acoustic performance in building design and construction. We will discuss the following key points. Firstly, acoustic and importance. Secondly, characteristics of audible sound. Next, behavior of sound in enclosures, defects due to reflected sound, common acoustical defects, general principles and factors in acoustical design and sound insulation. Now, we will introduce acoustic. What do you mean by acoustics? Acoustics is the science of sound. It deals with the origin, propagation and auditory perception of sound. It involves designing and constructing buildings for optimal sound and conditions. What is importance of acoustics? It is essential for designing theatres, cinema halls, auditorium, conference rooms and hospitals. It aims to minimize or insulate unwanted noise. Basically, sound is produced when a surface vibrates, creating waves of compression and rarefaction in the air. These waves cause the eardrum to vibrate and the brain interprets these vibrations as sound. When sound waves are periodic, regular and continuous, they produce a pleasant effect that is known as musical sound. In contrast, non-periodic, irregular and short duration sound waves create an unpleasant effect known as noise. Noise is an abrupt, complex sound with irregular periods and amplitudes originating from a source with non-periodic motion. Now let's discuss some of the characteristics of audible sound. Sound travels as waves consisting of compressions and rarefactions through a medium. These sound waves are longitudinal, meaning the particles of the medium move back and forth in the same direction as the wave. The speed at which sound travels depends on the medium's properties and temperature, moving faster in solid and liquid than in air. In air at 20 degrees Celsius, sound travels at 343 meter per second. In pure water, it travels at 1450 meter per second, while in bricks and concrete, it travels at 4300 and 4000 meter per second respectively. Sound cannot propagate in a vacuum, and for sound to be heard, there must be a continuous path of elastic material between the source and listener's ear. There are basically three characteristics of sound. First one is intensity and loudness. Second one is frequency and pitch. And lastly, quality of timbre. First one will discuss about intensity and loudness of sound. Intensity is the amount of energy a sound wave transmits per unit time through a unit area, perpendicular to its direction of travel. Mathematically, the intensity is proportional to the square of the amplitude of the wave, that is, I is proportional to A square. Loudness, however, is the perceived strength of a sound, influenced by the intensity and the ear's sensitivity. It does not increase linearly with intensity, but rather with its logarithm. According to the Weber and French laws, L is directly proportional to log I, which states that the perceived magnitude of a sensation is proportional to the logarithm of stimulus causing it. Intensity is a measurable physical quantity independent of the listener's ear, while loudness is subjective and can vary with the listener and the sound frequency. The loudness range perceived by the ear is vast. If two sounds of intensity I1 and I0 have loudness level L1 and L0, their difference in loudness intensity level is given by L is equal to K log of 10 I1 by I0, where K is constant depending on the units used. Loudness is measured in bells, but because bells are large unit, the decibel, which is the 1/10 of bell, is more commonly used. Thus, the formula for decibel is log L is equal to 10 log 10 I1 by I0 into decibels. The unit is decibel. A change of 1 decibel corresponds to a 26% change in intensity. The smallest difference usually detectable by the ear. For example, if a sound is 100 times more intense than another, it differs by 20 decibel. If it is 1000 times more intense, it differs by 30 decibel. The loudness corresponding to the threshold of hearing is 0 of this scale, while 130 decibel is the threshold of painful hearing. The following table gives the rating of intensity of sound in decibel. For example, threshold of audibility. Intensity level is 0 decibel. Threshold of feeling is very faint. Next example is rustle of leaves, whisper and proof rooms. Its range is 0 to 20 decibel and average is 10 decibel, but the threshold of feeling will be very faint. Next is quiet living rooms, private office, quiet conservation, average auditoriums. Intensity level, that is range, will be between 20 to 40 decibel and average would be 30 decibel and threshold of feeling will be faint. Likewise, if we move on to last portion, that is loudest sound due to pneumatic drills or aeroplane at a distance of 4 meter, then range would be 120 decibel to 140 decibel and average would be 130 decibel and the threshold of feeling will be pain and discomfort. The sound pressure corresponding to the threshold of hearing is about 0.0003 dyne per centimeter square and that corresponding to the threshold of pain is about 300 dyne per centimeter square. For example, radio and TV studios noise level range would be 25 to 30 decibel. If there is a music room, then noise level range would be 30 to 35 decibel. If there is hospital and auditoria, then noise level would be 35 to 40 decibel. And if there is a restaurant, the noise level range would be 50 to 55 decibel. Now, we will discuss about the second characteristics, that is frequency and pitch of sound. Frequency or pitch is the number of cycles a sound wave completes in a given time. It determines the quality of sound and allows us to distinguish between a shrill and a deep sound, even if they have the same intensity. The sensation of pitch depends on the frequency of vibrations reaching the ear. Higher frequency correspond to higher pitches. The frequency scale ranges from 20 to 1500 cycles per second. Next characteristic is quality or timbre. The quality of sound distinguishes different sounds with the same pitch and loudness, such as notes played on different instruments or produced by different voices. This is because sounds are rarely pure tones. They consist of a fundamental frequency and additional overtones. The quality of sound is determined by these overtones' presence, absence, strength and pitches. Recognizing different sounds such as voices, speech sounds, musical instruments and animals' calls if possible because of the memory of these tonal qualities. Next, we will discuss about the behavior of sound in enclosures. When sound is produced in a room, the short distance between the sound source and the walls means that there is a little to no reduction in sound due to distance. When sound waves hit the room surface, three things occur. Firstly, some of the sound is reflected back into the room. Some of the sound energy is absorbed by the surface and listeners. Thirdly, some of the sound waves cause the walls, floors and ceilings to vibrate, allowing sound to be transmitted outside the room. The amount of sound that is reflected or absorbed depend upon the surfaces, while the sound transmitted outside the room is influenced by the sound insulation properties of the surface. Now, we will be discussing about reflection of sound. So, sound waves reflect off large uniform surface in a similar manner to light waves, where the angle of incidence equals the angle of reflection. This phenomena can enhance the loudness and overall quality of sound. Key characteristics of sound wave reflection include: firstly, the laws of reflection. Sound waves generally follow the same reflection laws as light waves, although there are exceptions. Caution is needed when applying these laws. Secondly, wavefront from flat surface. When the sound waves reflect off a flat surface, the reflector wavefronts are also spherical with their center of curvature acting as the sound source images. Reflection from convex surface. Sound waves reflected off convex surfaces are magnified and spread out, making them weaker. Convex surfaces are useful for disturbing sound throughout a room. Reflection from concave surfaces. Sound waves reflected off concave surfaces are focused and amplified, resulting in a concentrated effect at specific points. Concave surfaces can be used to intensify sound in particular areas. Next, we will deal about some of the defects due to reflected sound. The behavior of reflected sound is crucial in the main acoustical design of enclosed spaces. Two main issues that can arise from sound wave reflections are echoes and reverberations. Firstly, we will discuss about echoes. An echo occurs when a reflected sound wave reaches the ear after the original sound has been heard, causing a repetition. The sensation of sound persists for about 1/10 of a second after the source stops. For an echo to be perceived as distinct, it must reach the ear at least 1/10 of a second after the direct sound. Since the speed of sound is 340 meter per second, this means the sound must travel at least 34 meters, making the reflecting surface's minimum distance from the source 17 meters. If the distance is less, the sound appears prolonged. Near echoes, which can blur sound, happen when the reflecting surface is between 8 to 17 meters away. Multiple echoes may occur when sound reflects off several surfaces, such as two parallel cliffs. The rumbling of thunder is due to successive reflection from clouds, mountains, rocks, and atmospheric layers. Next, we will discuss reverberation. Reverberation is the persistence of sound in a hall or auditorium after the source has stopped due to multiple reflection in the space. This is common in cathedrals and unfurnished new rooms where reverberation can last up to 10 seconds. While some reverberation adds richness to music, too much is undesirable. Reverberation time is the duration the sound persists in space, measured as the time it takes for sound energy to decrease by 60 decibels or to 1/10 of its original intensity after the source stops. Sabine's expression for reverberation time. Actually, the Professor W.C. Sabine from Harvard University extensively studied architectural acoustic and reverberation time. He found that reverberation time varies inversely with the effective surface area and directly with the room's volume and is independent of the source, listener's position and room shape. Sabine developed an expression for reverberation time as T will be equal to 0.16 V divided by alpha 1 S1 plus alpha 2 S2 plus alpha 3 S3 and so on. T will be equal to 0.16 V divided by sigma ds, or it will be equal to 0.16 V upon A, where T is equal to reverberation time in seconds and V is volume of the room in cubic meters, where alpha 1, alpha 2, alpha 3 are absorption coefficient of individual surfaces, for example, walls, floors, ceilings, etc. S1, S2, S3 are the area of individual absorbing surfaces, and capital A is total absorbing power in meter square. The table showing gives the relation between reverberation time and acoustic of a room. For example, if the reverberation time in second is 0.5 to 1.5, then acoustic would be excellent. If it is 1.5 to 2, it will be good. If it is 2 to 3, it will be fairly good. If it is 3 to 5, it is bad, and above 5, it is very bad. Indian Standard Code, that is IS 2526/1963, recommends to use the following figure for the determination of reverberation time for various size of enclosed space and for various purpose and use of spaces. This figure illustrates the optimal reverberation time at 500 Hz for various types of rooms, plotted against room volume in hundreds of cubic meter. This graph is used to determine the desired reverberation time based on the room's purpose and size as per the guidelines set by Indian Standard Code 2526/1963. The lines on the graph represent different settings. For example, the line labeled speech indicates optimal reverberation time for environments where clear speech is crucial, such as lecture halls. School auditoriums and motion picture theatres have their respective lines suggesting slightly longer reverberation times to enhance the auditory experience in these larger spaces. The average for music line shows the longest reverberation time suitable for music performance spaces where enhanced acoustic add to the quality of sound. The graph shows that as the volume of room increases, the optimal reverberation time also increases. This graph helps architects and acoustical designer to tailor the acoustic of a room to its intended use by choosing materials and design strategies that will achieve these optimal reverberation times. Following table gives the optimal reverberation time and audience factor for acoustical design. For example, cinemas theatre optimal reverberation time is 1.3 second and audience factor is 2/3. For churches, optimal reverberation time is 1.8 to 3, audience factor is 2/3. So on, if we go to public lecture hall, then optimal reverberation times is 1.5 to 2 and audience factor is 1/3. So this audience factor mentioned in the context of optimal reverberation times refer to the proportion of room's seating capacity that is expected to be occupied during use, which impacts the acoustical characteristic of the space. Different types of room and events have varying ideal occupancy rates for optimal sound quality. For example, cinema theatres, the audience factor of 2/3 suggests that optimum reverberation time calculation assume that about 2/3 of the seating will be occupied during typical movie screenings. This occupancy affects the absorption characteristic of the space as more bodies and clothing absorb sound, reducing reverberation. Churches, here the factor ranges from 2/3 for the regular services to potentially fuller during special events. The higher the occupancy, the more sound is absorbed, and this needs to be considered in designing for reverberation to ensure clarity and richness of the sound. Next important topic to be discussed is absorption. When sound waves hits a surface within spaces like auditorium or halls, some of the energy is absorbed in various ways. For example, through the air, by the audience, in furnishings, and at surfaces like walls and ceilings. So, we will discuss one by one. First, we will take up the absorption in the air. This occurs as sound waves travel through the air, causing friction among oscillating molecules. Through this effect is minimal. Second one is absorption by the audience. The clothing worn by people in the audience absorbs sound, with more absorption in colder months due to heavier clothing. Next is absorption in furniture and furnishing. Items like furniture, curtains and carpets significantly absorb sound. Next is absorption by boundary surfaces. Sound waves absorbed by walls, floors and ceilings can penetrate porous material, causing vibrations or resonation within the material, and some energy is lost through molecular damping and structural transmission. Water absorbents. Special materials used on boundary surfaces to increase absorption are known as absorbents. The ceiling is generally more exposed to direct sound waves that are other surfaces and is usually the largest single area available for treatment. Absorbents can be broadly classified into following. First is porous material, resonant panels, cavity resonators, composite types, etc. We will take on types of absorbent one by one. First is porous material. These include items like rock wool and curtains, which primarily absorb higher sound frequency through friction caused by air movement within the material. Next is resonant panels. These panels reduce sound by damping vibration within the panel effectively, mostly at lower frequencies. Next is cavity resonators. These are the structure designed to absorb sound at various frequency through the resonance of air within them. Composite absorbers. These newer designs combine features of porous material, resonant panels and cavity resonators to absorb sound across a broad frequency range. Some of the common sound absorbing materials are material like acoustic plaster, compressed cane, wooden fiber boards and minerals or glass wools are typical absorber used in construction. When in most venues, the audience itself is a significant absorber of sound, especially at higher frequencies. Thus, to manage sound across all frequencies, low frequency absorbers like wooden paneling are also used on walls and ceilings. Area prone to causing disruptive sound reflection, such as the rear walls or balcony parapets, should be specifically treated with sound absorbing materials to ensure sound reaches all parts of the hall uniformly and without delay. Absorption coefficient and measurement of absorption. So, our topic is here to find the absorption coefficient and how we will measure it. The effectiveness of sound absorber is determined by both its size and material efficiency. This coefficient represents the ratio of sound energy absorbed by a material to the sound energy that hits it. The standard unit of sound absorption is named the Sabin, in honor the scientist who defined it. 1 meter square of a fully opened window absorbs sound at a rate defined as 1 meter square Sabin, as it is assumed that sound passes completely through an open window. Therefore, the absorption coefficient for an open window is considered to be 1. For the materials, the absorption coefficient is the ratio of the sound absorbed by the material to that absorbed by an open window. The absorption of a surface is calculated by multiplying its area by its absorption coefficient, resulting in a value expressed in meter square Sabins. Now, to calculate the total sound absorption, that is A, of any venue like hall or auditorium, you sum up several factors like the product of air volume and its absorption coefficient, the combined absorption of all surfaces based on their area and specific absorption coefficient, the total absorption of any unoccupied upholstered seats, and the absorption contributed by the number of people present using an average absorption coefficient per person. This total absorption figure is then used to calculate the hall's reverberation time using specific equation. If the calculated reverberation time isn't within desired limits, adjustment to the total absorption are made to achieve the target. Research has established the absorption coefficient for various materials at different sound frequency, usually averaged over low, medium and high frequency, namely 125, 500 and 2000 cycles per second. These coefficients for various building materials and furnishings are typically listed in reference tables for practical use in acoustical design. Now, we will see what are the requirements of a good acoustic material. Let us see one by one. Firstly, it should have high coefficient of absorption. It should be efficient over a wide range of frequency. It should be relatively cheap and easily available. It should be pleasing appearance after fixing. It should be self-supporting and should afford easy fixing. It should be fire resistant. It should have sufficient structural strength. It should be heat insulating and non-hygroscopic. It should be durable and should not liable to attack by insect, termites, etc. Some of the common acoustical defects, let us see one by one. Achieving perfect acoustical condition in large spaces such as rooms, halls or auditoriums requires clear sound throughout the occupied area without echoes, near echoes or distortion, and with the correct reverberation time. Here are some common acoustical defects often encountered along with recommendation for addressing them. First is reverberation. This is the continuation of sound in an enclosed space even after the sound source has stopped, typically due to inadequate absorption. While some reverberation enhances sound quality, excess reverberation can cause overlapping sound and confusion. Optimal sound clarity is achieved by adjusting the reverberation time with appropriate absorbent materials. Next is echoes. Echoes, as we discussed, occur when sound reflects off surfaces that are more than about 17 meters away, particularly in rooms with curved smooth surfaces. To mitigate echoes, the room shape should be carefully considered and rough porous interior surface should be used to disperse echo energy. Next is sound foci. This issue arises when concave surface focus reflected sound waves at specific spots, creating intensely loud areas known as sound foci. This can be addressed by using geometrically designed interior shapes and applying highly absorbent material to these focal areas. Next is dead spots. It is related to sound foci. Dead spots are areas where the sound intensity is too low due to the concentration of sound elsewhere. Installing diffusers can help achieve a more even distribution of sound, eliminating these quiet zones. Next is insufficient loudness. If sound does not adequately reach all areas of hall, it may be due to lack of reflective surface near the sound source or too much absorption. Adjusting the balance between reflective surface and absorptive material can optimize reverberation time. In large halls, strategically placed loudspeakers can also help. Next is exterior noise. Noise from outside source like traffic or industrial operations can disrupt indoor acoustics. This can be reduced by strategically designing the building in relation to its surroundings and enhancing the sound insulation of exterior walls and openings. Now, we will take acoustical design of hall. What is the condition for good acoustics of a hall? We will discuss one by one. The initial sound from the source should be of adequate intensity so that it can be heard throughout the hall. For halls of big size, suitable sound amplification should be installed. The sound produced should be evenly spread in the hall so that sound foci and dead spots are avoided. The boundary surface should be designed that there is no echoes or near echoes. The boundary surface of the hall should be properly designed so that the desired reverberation time is achieved and unwanted sound is absorbed. The absorbent material should be distributed evenly over the wall surfaces of the hall. In case of the conference hall, the acoustics of the hall should be so designed so as to ensure proper conditions for listening, assuming that the person may speak or listen from anywhere in the hall. In the case of music hall, the treatment should be such that the initial sound reaches the audience with the same intensity and frequency. And the last, the outside noise should be properly insulated. Now we will take some of the general principles and factors in acoustical design. First is site selection planning. Choosing the right location for an auditorium or hall is heavily influenced by the surrounding noise level. It is vital to perform a noise survey to identify the quietest possible area, as this can prevent the need for extensive and expensive soundproofing measures. For spaces without air conditioning, where doors and windows are left open, minimizing external noise through strategic site location is particularly important. In facilities with air conditioning, efforts should be made to reduce noise from the system itself. The aim is to structure and orient the building to maintain interior noise level at or below 45 decibel, creating a conducive environment for performances. Next is dimension size. The dimensions of an auditorium should be tailored to accommodate the expected audience size and the acoustic needs specific to its use. Larger spaces are required for music hall to allow sound to effectively fill area, while lecture hall benefit from smaller volume to enhance quieter sound. The floor space should be planned with 0.6 to 0.9 square meter per person, considering aisle space for excluding the stage area. Factors like ventilation, needs, the presence of balconies and the type of events hosted influence the optimal ceiling height. which should range from 6 meter in smaller venues to 7.5 meter in large ones. Now, we will discuss about shape. The shape of a hall or auditorium is vital for acoustical design as it helps address issues like echoes, sound foci and dead spot. A fan-shaped layout is preferred to improve sound clarity throughout the space. The side wall should be angled no more than 100 degrees from the curtain line to ensure proper sound synchronization and visual clarity, especially in theatres and cinemas. This setup ensures that the audience can clearly see and hear performance with the farthest seats ideally no more than 23 meters from the stage, allowing viewers to distinguish facial expression and line sound with visual cues. Now, we will take seats and sitting arrangement. Seats in an auditorium should be arranged in concentric arcs from the curtain line, maintaining an angle of no more than 30 degrees between the highest visual point and the horizontal. For dramas, the first row should be 3.6 meters from the stage. For cinemas, at least 4.5 meters. Seat width should be 45 to 56 centimeter with a back-to-back distance of 45 to 106 centimeter. Seats should be staggered for clear visibility with upholstery for consistent acoustics. Rows should rise 8 to 12 centimeter towards back and the floor should incline at least 8 degrees. In balconies, the extension should be within twice the balcony recess height with the line of sight within 30 degrees of horizontal. Install reflector to address sound shadows in deep balconies. Now, the treatment of interior surfaces. Ceiling and walls should enhance sound reflections. Rear walls should be flat or convex, avoiding concave shape unless corrected with spade or convex features. In fan-shaped halls with non-parallel walls, they can be reflective if needed. For parallel side walls, leave them untreated for up to 7.5 meter from the proscenium end. Reverberation and sound absorption. Balance reverberation to enrich music without excess. Adjust reverberation time with the absorber based on hall use and audience size. Calculate need absorption using A1 is equal to A minus A2, where A2 includes existing absorption from furnishing an audience. Use low frequency absorber for a broad frequency range and ensure upholstered seats for consistent acoustic. Treat reflective areas like rear walls and balcony parapets with sound absorbing materials and distribute additionally absorption evenly. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. The second portion of our topic of this session, that is sound insulation, we will deal it in our next further sessions. Thank you for attention in this session. See you in the next class. Thank you.